In this video, we're going to look at section 4.1 and look at how you'd get started. So let's go to our first question from section 4.1, which is a spherical snowball is melting in such a way that its diameter is decreasing at a rate of 0.3 centimeters per minute. Assume the snowball remains perfectly spherical as it melts. At what rate is its volume decreasing when the diameter is 17 centimeters? And round your answer to 3 decimal places. Well, let's see how we should get started on this. Oh, so I copied this from the, and it copied it weird, so we'll just stop that. The first thing we need to do when we are looking at related rates is to assign symbols to all the variables involved in the problem and draw a figure if we think it will help. So we have a spherical snowball like that. Oh, lovely. And the diameter is decreasing at a rate of 0.3 centimeters per minute. So the diameter. So I'm gonna let D be the diameter. And because it says it's decreasing at a rate of 0.3, and again, I copied it and it did weird stuff. So 0.3 centimeters per minute, that's a rate. So we're going to write D, the derivative of the rate with respect to time is going to be 0.3 centimeters per minute. Assume the snowball remains perfectly spherical. At what rate is the volume decreasing when the diameter is 17 centimeters? So we want to find the decrease in volume, which would be dV dt. And that's when D is 17 centimeters. So what relates, so that's what we would do first. That's our first step, is to identify what we're given and what we want to find. The second step is to find an equation. Well, it's the third step really, but find an equation that relates these. So we look at our formula sheet that I put in the announcements yesterday, and we find that volume is 4/3 pi r cubed. You don't have to have that memorized. If you do, that's better, but if you don't, that's fine. So this is what we need, but we're not given radius, we're given diameter. So we're going to change these things to radius. So if the diameter is decreasing at 0.3 centimeters per minute, you'd probably want to change this to the change in radius, which would be half that because radius is half diameter. So it would be decreasing at 0.15 centimeters per minute. And instead of when the diameter is 17, you're going to look at when the radius is not 17, but 8.5 centimeters. And then you're going to go ahead and take the derivative here. You only have one variable, so it should be easy. You'll take the derivative implicitly and find the rate at which the volume of the snowball is decreasing. All right, let's, that kind of helps you set it up, and that's what you want to do for every problem. Let's see if how problem 2 looks. Let's go here. All right, question 2. Your question 2 will probably be similar to this one. It says an airplane is flying at an elevation of 4,800 feet. A man is 3,800 feet from base of a radio tower. The airplane flew over the man, heading in the direction of the radio tower. If the plane is flying at a rate of 650 feet per second, how fast is the distance between the man and the plane increasing when the plane passes directly over the radio tower? Round your answer to 3 decimal places. Well, we know first we want to assign symbols and variables to be involved in the problem. I would probably draw the picture. So you have a plane that is 4,800 feet above the ground. And let's draw a plane. Yeah, okay, there's my plane. And it's going that way. And then it's going to pass over a radio tower here. And here's a guy that's going this way. So we're going to draw a triangle to relate these things. We're going to say, here's the guy, there's the tower, and there's the distance. It says that, let's see, a man is 3,800 feet from the base of a radio tower. So this is 3,800 feet. The plane is 4,800 feet above the ground. And the distance between the man and the plane is going to be represented by the hypotenuse of this right triangle. And we'll call that C because it's the hypotenuse. You could call it D because it's distance. And when I'm doing problems like this, I usually let the horizontal distance be X and the vertical distance be Y because we're used to looking at X and Y, but you can do anything you want. So that is helpful because it gives us a basis to start with our problem. There is an easy relationship between these three pieces, the Pythagorean theorem, and you can find out C using that. You'll probably need that. And then let's identify things. So if we're calling X 3,800, that's fine. Feet, and Y is 4,800 feet in my problem. The plane is flying at a rate of 650 feet per second. So that's up here, but that's the same as the horizontal distance here. It's a horizontal rate of change. So we're going to say since X is our horizontal measurement, that speed of the plane is dx dt. And that would be the 650. Then you're going to use a relationship relating these variables to find C and to find the rate of change. It says, how fast is the distance between the plane increasing, between the man and the plane increasing when the plane passes directly over the tower? So you want to find how fast C is increasing. So we're going to call, since that's a rate, we want to find dc dt. So again, it's really critical to be able to set up the problem. Let's look at how we might set up question 3. Question 3 says the length of the rectangle is increasing at a rate of 7 centimeters per second, and its width is increasing at a rate of 3 centimeters per second. When the length is 30 and the width is 20, how fast is the area of the rectangle increasing? This is just like a problem we did in class, so I'm going to trust you guys will be fine setting that one up. And let's look at our shadow problem. We started this in class yesterday, and I was thinking we needed to use tangent, but we discovered that it was much simpler than that. So we're going to work at setting this one up and see if that can be helpful. In question 4, it says a spotlight on the ground is shining on a wall 16 meters away. Again, I didn't get rid of the duplicate. If a woman 2 meters tall, very tall woman, walks from the spotlight toward the building at a speed of 1.2 meters per second, how fast is the length of her shadow on the building decreasing when she is 6 meters from the building? Round your answer to 3 decimal places. Okay, so we want to know how fast her shadow is decreasing. If we drew another little gal here, another little person who's not little, she's very tall, but if she was here, then her shadow on the wall would be smaller. So this shadow is decreasing. That's what this problem is talking about. Is that an eraser? Let's erase this person. Okay. So let's see what we know. We know that the wall is 16 meters away from the spotlight. So that distance is 16. The woman is 2 meters tall and walks from the spotlight toward the building at a speed of 1.2 meters per second. So that's a speed, that's going to be a derivative. How fast is the length of her shadow on the building decreasing when she is 6 meters from the building? So here when she's 6 meters from the building. So I didn't really draw this super to proportion, but if this is 6, that would mean if the whole length is 16, this little length here would be 10. Now, I was thinking that we needed to use trigonometry to relate this distance to the wall distance, tangent being the opposite over the adjacent, but it's much simpler than that. After exploring it a little further, we can use ratios of similar triangles. When you were in geometry or maybe some point in your life, you learned that if triangles are similar, if I call this triangle A, my big triangle is ABC, and my smaller triangle here is, let's call that D and E. We'd say that ABC would be similar to triangle ADE. And similar triangles have proportional sides. So if this length here is 10 and she is 2, then this big length here would be 16, and this would be X there. We could certainly find it using that proportion. So let's see what we need to do here. So we have this relationship, which I've redrawn over here, and we want to set up a proportion. And the small triangles, that's not working. There we go. The small triangle sides will be proportional to the large triangle sides. So we could go x is to 2, x is to 2, as 16 is to y, because similar triangles have proportional sides. You could have also said x was to 16. The small side is to I'm sorry, the bottom side is to the bottom side, as the 2 would be to y. But in either instance, the way we would solve this using the cross product, you'd get x times y is 32 here, and here also you'd get x times y is 32. So the formula we want to use is x times y is 32. Now when we take the derivative, we have to use the product rule. So you'll take the first times the derivative of the second plus the second plus the second times the derivative of the first. And the 32 will become 0 when you take the derivative. One thing I did forget is the 1.2 meters per second. 1.2 meters per second is the woman walking towards the wall. So her distance is increasing. And we'd say, since her distance is represented by x, we'd say dx dt is 1.2 meters per second. And we want to find how fast the shadow is decreasing. So if the shadow is y, I usually let vertical distances be y, we want to find dy dt. And then you'll plug the numbers that we have in here, and you can find y using the proportions, because let's see, 10 would be to 2, as 16 is to y. Taking the cross product will help you solve for y here. All right, so that one was a little involved. I hope that is helpful. Let's see how they go from here. On this one, this is number 5. A cylindrical silo is being filled at a rate of 5 cubic meters per minute. If the diameter of the silo is 4 meters, how fast is the height of the grain increasing? Round your answer to 3 decimal places. Now you'll notice here, you'll want to use, since it tells us that we're increasing at 5 cubic meters per minute, we know that's a volume because it says cubic meters. Also, you're going to want to use your formula for volume of a cylinder, which you have in that handout or in that thing I put in the announcements, the reference material. Now, the radius of the silo is going to remain constant. So when you take the derivative, it's a number, and it doesn't factor into the problem. What's going to factor into the problem? Well, if you know, but it's a constant. So when you take the derivative, just know that the radius is a constant, and it will be 2 if the diameter is 4. Probably going to want to draw a problem, identify your rate there, and you want to find how fast the height is increasing. So that will be the rate that you want to find, and you'll set that one up on your own. Let's try this one. Related rate motorcycles. Two motorcycles start from the same point. Motorcyclist Y travels north at a rate of 18 miles per hour. There's a rate, so that's a derivative. Motorcyclist X travels east at a rate of 24 miles per hour. At what rate is the distance between the motorcycle, I'm sorry, at what rate is the distance between the motorcycles increasing 2 hours later? So let's start this one. We'll draw and we'll see if we can identify what we need to identify on it. So on this problem, again, we'd probably draw a picture. They start at the same point. One is driving north and one is driving east. The guy driving north is going at a rate of 18 miles per hour. And the person going east is at 24 miles per hour. So those are rates, and if we let north, we could use north and east. I usually use Y for vertical and X for horizontal. And those rates are increasing. So we're given that dy dt is 18 and dx dt, they both be positive because they're both increasing. So this is what we want you to do. We want you to set these up. They are increasing at a right angle, and we want to find the distance between the two. So if we call the distance d, we can. I'm going to call it c because, again, we have a Pythagorean relationship. We also know they've been traveling for 2 hours. So if they've been going for 2 hours at 18 miles per hour, you can find how far y has gone, and you can find how far x has gone. And those will be your side lengths. These are really dx dt. And this is dy dt. So you can find what those actual lengths for y and x are, and that will help you find c. And then you can use the relationship that you see there in order to solve the problem. I think that one's pretty straightforward. Let's see how the next one looks.